Okay, it's recording now.
Oh, I guess I should. Dave, can Ian share his screen, or how does it work?
I
Because
think I
I'm
set
not the
up so
host.
anyone can share.
Oh, I
Okay.
have it here. Okay,
Great.
let's try this.
Yeah.
Can you guys see this?
Yes, indeed.
Okay.
Yes. Should we start? Are you ready?
Yes.
It's my pleasure to introduce Ian Zemke from Princeton University. He's going to tell us about a mapping cone formula for involutive Heegaard Floer homology. Thanks. Cheers.
Great. Thanks for the introduction. Happy to see you guys here. It's nice to see some familiar faces. So today I'm going to talk about a project joint with Kristen Hendricks, Jen Hom, and Matt Stoffregen, studying involutive Heegaard Floer homology. I guess the date is wrong, but you can see the last date I gave this talk, I guess. So let's just begin with some recap of what all the terms of discussion are. So we're studying three manifolds, and kind of the most basic object that we're going to study is Heegaard Floer homology. And so if you take a spin C structure on a three manifold, Ojvath and Szabo tell you how to construct these groups or these chain complexes, which we take homology of, and we get these F adjoin U modules. U is just a variable. We take homology, and we get these modules, which we sort of know and love. And if Y is an integer homology 3 sphere, we have a knot in Y. It's often helpful. It's often really can be really good to study this sort of refinement of knot Floer refinement of Heegaard Floer homology called knot Floer homology. And we can actually think of this just as ordinary Heegaard Floer homology, the chain complex, but with an extra filtration associated to the knot. So kind of we take the chain complex for Y, we have a knot in it, and it gives us some extra structure on the chain complex. And there's a variety of ways of looking at this extra structure. One of them is just as a filtration on the ordinary chain complex. And it actually is kind of we have kind of this funny filtration where it's over two, we have sort of two components of the filtration. We say it's Z plus Z filtered. So here's an example of the trefoil. So this would be the trefoil complex, the knot Floer complex. And so we often draw the generators in the plane, depending on what their filtration level is. And the arrows kind of always go down into the left, like they increase both, they decrease filtration, or they're non-increasing, I guess. So there's the trefoil. And so one of the reasons that it's so useful to study knot Floer homology is that there's a mapping cone formula for surgeries. Kind of I think one of the main motivations for defining knot Floer homology, I mean, other than the fact that it's just this kind of like algebraically beautiful object that tells you a lot about topology, I think one of the places it came from was trying to compute the ordinary Heegaard Floer homology of surgeries. And so Ojvath and Szabo proved this sort of remarkable formula that if you have a knot in a three manifold, there's a way of computing the Floer homology of the surgery from the knot Floer homology of the knot. And it takes the form of a mapping cone formula. And A and B are sort of these gadgets built up from subcomplexes of CFK infinity, and they seem complicated. And this DN, this mapping cone differential, also kind of looks complicated, but it's for the most part, for knots in S3, it's completely computable, and it's not actually that challenging of a formula to get your hands to use. And so here, I guess some technical details, if you care. We're going to work with algebra gets subtle because for various reasons, and so here we're working with coefficients in the power series ring instead of just F adjoin U. I mean, there's some subtle technicalities that don't really conceptually, they're not conceptually that important. And as I kind of alluded to, when you have a knot in S3, all of the maps are just completely computable up to, say, an overall chain homotopy equivalence, as long as you know CFK infinity. So if you know CFK infinity of the knot, you can compute all the maps in the mapping cone formula. So that's great for applications because you can just compute the Heegaard Floer homology of all surgeries, as long as you know the knot Floer homology of the knot. And so I think I'd like to say a little bit more about what all of these gadgets are. So remember, we have this A and we have this B. What is A and B? Well, they're direct products of subcomplexes. So A, this bold A is a direct product of a bunch of A's. And so somehow it's actually sometimes easier to work with the plus version instead of the minus version. Because the plus version, you don't need these completions. You can work with direct sums instead of direct products. But basically, like, unless you are like an expert at trying to actually use the formula, you should just ignore all of that. And just, it's basically just a product of all of these A's and these product of these B's. And so actually kind of B, the B's are just totally independent of S. So it's a direct product over Z of Z copies of just one group. And the actual homology of that group is just CF minus of the underlying 3 manifold. There's no knot data in there. It's just, so for knot in S3, each B is just homotopy equivalent to S3. So you've taken Z copies of these. And then I'm going to tell you what the A's are now. The A's are a little more subtle. So kind of like the B's, they actually are kind of these, you have this filtration. And so the B's are kind of like one of the half planes of this filtration, like all the generators in this half plane. And the A's, A sub S is, it's a quadrant, but it's shifted. You allow like one sort of region of you allow one of the boundaries of this quadrant to depend on S. So it could have different heights, but it's just like all the generators in this quadrant. This is a very simple description of it. And so A sub S is a subcomplex. Here I write it out in words. And B sub S is this half plane. So there's these two simple things. And there's one important thing is A sub S is actually a subcomplex of B sub S. And so, if something is a subcomplex, you can kind of turn that into a map by saying, we're going to look at the inclusion map from the small one to the big one. And so in the actual mapping cone, the differential has this flavor. It's a sum of 2 maps, V and H. And I'll tell you what those 2 maps are. V is a map which sends A sub S to B sub S. H sends A sub S to B sub S plus 1. So V is just an inclusion. As I mentioned, there's this canonical inclusion. So one of the maps is just you include. And then H, it's slightly different. Oh, here's a picture. So it's slightly different. You include you take A sub S and you include it into the other half plane, which I will call B sub S tilde. So we have 2 half planes. We have B sub S, which has no dependence on S, and we have B sub S tilde, which is this other half plane. And kind of for abstract reasons, you know that there's some homotopy equivalence from the tilde B sub S to the ordinary B sub S. And so kind of the mapping cone differential H is a composition of an inclusion followed by a homotopy equivalence. And for knots in S3, basically that homotopy equivalence is just determined algebraically, for algebraic reasons, there's no kind of indeterminacy in this homotopy equivalence. And so we can always just pick any F you want and you can build the mapping cone. And it's well defined, just for there's not enough room in the Heegaard Floer homology of S3 for there to be any indeterminacy. Okay, so this is kind of, the goal is to do this here's a diagram, kind of what it looks like. So we have the A's and we have the B's. The A0 goes to B0, and so V preserves the index, and H increases the index by 1. So that's the formula. I mean, that's the mapping cone formula. And the goal of this whole project is to construct an involutive version of this mapping cone formula. So as I mentioned, for knots in S3, you can just completely compute. You can always compute this mapping cone, all the maps in it for knots in S3. And the point is that all of the maps were just canonical maps, except for one, which was this homotopy equivalence. And in this homotopy equivalence, we had to make a choice. But like if you think about it, it's a homotopy equivalence between f adjoining u and f adjoining u. And there's really only one of those. I mean, technically, it's a homotopy equivalence between complexes, which are homotopy equivalent to f adjoining u. So in practice, there might be more than one, but they're all homotopic. And so there's just not enough room to have, there's not enough room for there to be anything like other than with homotopy type other, with two different homotopy types. So you can, that's one of the reasons this mapping cone formula is so useful, is that you can actually just compute always the maps in it up to an overall homotopy equivalence of chain complexes. So our goal is to do this for involutive Heegaard Floer homology. What can we say? We want to upgrade this program one step. So what is involutive Heegaard Floer homology? Well, suppose we have a 3-manifold with a spin C structure which is conjugation invariant. You have this conjugation action on spin C structures. There's a variety of ways to describe this. There's sort of this Toraya's interpretation of spin C structures as vector fields on manifolds. And then the conjugation action is you just take the vector field and you multiply it by -1. So like there's all these different ways of looking at it. But there's this sort of canonical conjugation action, and kind of a self-conjugate spin C structure is basically this morally the same as a spin structure. It's not quite one-to-one correspondence, but you can write down what it is like. But morally, they're the same. Self-conjugate spin C structures are sort of in correspondence with spin structures. So you can think of this as a 3-manifold with a spin structure. And note that every, for an integer homology 3-sphere, there's only one spin C structure. So automatically it's self-conjugate. So kind of sometimes the best situation to look at is just for integer homology 3-spheres. So there's this homotopy involution on the ordinary Heegaard Floer complexes that Hendricks and Manolescu studied. If you have a self-conjugate spin C structure, and they call it iota. And there's a way to describe this. Basically, if you take a Heegaard diagram, there's this canonical conjugate Heegaard diagram, which is basically the same surface, but you change the orientation of the surface. And then you just leave the alphas and betas the same. But if you think about it, kind of their role in the whole picture has switched. Like the alpha handle body, now you should call it the beta handle body. So we indicate that by switching out the ordering of alpha and beta. There's this canonical chain isomorphism, which sends from the H bar complex to the H complex, which you just send an intersection point to itself in the diagram. Like you don't do anything, you just, it's like the diagram hasn't changed, you've just like turned the paper upside down.
So Ian, H bar is that's the same oriented 3-manifold as H, right?
Same oriented 3-manifold, that's right. Yeah, that's right. You've changed the orientation of the Heegaard surface, but not of the 3-manifold. That's right, thanks, Dave. Exactly.
So you change the orientation of the surface, but then you also change the order of beta alpha. So either one of them would change the orientation of the 3-manifold, but together they don't.
Exactly, that's right. So there's kind of these two operations. There's changing the orientation of the surface and changing the order of the alphas and betas. And doing just one of those changes the orientation of the 3-manifold. But then if you do both of them, that fixes the orientation of the 3-manifold. That's right, exactly. Yeah, so there's a lot of these like symmetries and dualities that are going on here. And so it's very like, it's a very like, that you have to do it just exactly this one to do the conjugation symmetry. And then, but, kind of from naturality, Heegaard Floer homology is independent of the Heegaard diagram. So if you pick two Heegaard diagrams for the same 3-manifold, there's some set of moves, Heegaard moves, like stabilizations of the surface, handle slides, and isotopies, and there's some set of moves which will take you from one to the other. And so, these are two perfectly valid Heegaard diagrams for the same 3-manifold, so we can connect them by some horribly complicated set of Heegaard moves. And so the involution, we want an endomorphism of just one complex. We don't want an isomorphism between two different complexes. We want an endomorphism of one. So we take the composition. we first go from one Heegaard diagram to its conjugate via the sequence of moves, and then we do this canonical isomorphism, eta. Now that was Hendricks and Manilescu's construction to define an involution, an endomorphism of one chain complex. So the involutive chain, the involutive Heegaard Floer complex, the chain complex, they define it just as the mapping cone of the identity plus this involution iota. And we always add in this extra Q variable, which is sort of a formal thing. We just say it's a formal variable that we just put on the codomain. And the reason we put it on the codomain is that it gives us a nice module structure. We think of it as a module over F adjoin UQ mod Q squared, where Q just kind of takes the domain of the mapping cone to the codomain of the mapping cone. So you kind of upgrade it to a chain complex over this, a free chain complex, free finitely generated chain complex over this bigger ring. And so it's had some nice applications of the homology cobordism group. I mean, prior to this work, Dye, Hom, and Stoffregen and Trong, amongst other things, they showed that there's a Z infinity summand of the homology cobordism group. Previously, it was known that there was a Z infinity subgroup. So that's due to Fintuschel and Stern and Furuta independently from about 1990. So 30 years ago or so, they proved that. So it's a difference between a subgroup and a summand, I guess. So depending on algebra, what your views are, this is either a great step forward or just, what is the difference between a summand and a subgroup? But I mean, that's a hard thing to do, right? Like to show that there's a summand algebraically. You have to construct homomorphisms, not just, and so they constructed homomorphisms from the homology cobordism group. And so it's this kind of, and so kind of the philosophy is that like, if you have F adjoin U, if you have a invariant over F adjoin U, the only real, like if you have ordinary Heegaard Floer homology, the only real homology cobordism invariant you could look at would be the D invariant. That's the only invariant of homology cobordism, like algebraically, that you could abstract, that you could sort of take out of this invariant. But once you just add in like the tiniest bit of extra algebraic information, like this Q action, now you just have like so much, you can see so much more. And so the D invariant is one homomorphism, but actually what Dye, Hom, and Stoffregen and Trong did is they defined kind of infinitely many homomorphisms out of the homology cobordism group. And so that gives you kind of a, it's like a whole, an infinite dimensional, set of invariants that instead of just a one-dimensional set. And so kind of just from one additional variable, you get a huge amount more information. So anyways, that's kind of one thing that is one of many things that has been that the involutive Heegaard Floer homology has been able to say about the homology cobordism group. So here's a general question: is how do we compute Heegaard Floer homology? How do we compute involutive Heegaard Floer homology, HFI minus? So, a leading example, is there a mapping cone formula? I mean, we, in sort of very gory detail, talked about the ordinary Heegaard Floer map, the ordinary not surgery mapping cone formula, so that we would have some language to talk about, at least understand roughly what the maps are. And so here's some previous results towards this. So they're kind of in their original work, Hendricks and Manilescu defined this not involution, which is an involution. It's actually not an involution, but it's an endomorphism of CFK infinity. It's not an involution because it doesn't square the identity map, but it has a very predictable square. It squares to something that's very easy to understand. And so what they proved and so we call it an involution kind of for cultural reasons, but it's technically not an involution, but it's a helpful endomorphism. We say that, So one of the things they proved was this large surgery formula. They proved that if you do a sufficiently large surgery, like if the coefficient is sufficiently large, then in the sort of zero spin C structure on the surgery, the involutive Heegaard Floer complex, which I'll write as like CF minus with the involution. This is homotopy equivalent as an iota complex to just A0, the ordinary large surgery complex with the not involution iota K. So it's basically as simple as you could hope for the large surgery theorem. And so in particular, you can compute this is just kind of restating the definition using the above, the sort of formula above, that if you want to compute the chain complex of HFI minus, that's going to be the homology of the mapping cone at A0 with this involution, identity plus iota K. So that was kind of the first thing that lets you compute a lot of examples. One downside of this is that this formula is that you usually will not be able to compute the invariance of integer homology 3 spheres using this, because n has to be large. The only time it's a homology sphere is when n is equal to plus or minus 1. And so generally you're not, I mean, I think for some knots you can get away with it, like some very small knots, but typically you're not going to be able to compute surgeries using this formula. And so we need a sort of more robust way to compute. And I guess here I say explicitly 0, if you notice in the brackets, there's a square bracket 0. It's the spin C structure identified with 0 under, there's a canonical identification spin C of the surgery with Z mod n. And so this is the 0, 1. There's some way to identify those. And it's self-conjugate. It's the conjugation action is like on Z mod n is like I maps to minus I. So another step which led to a lot of computations was due to Hendricks and Lipschitz. They used bordered Heegaard Floer homology to compute HFI hat of y, the hat version where you set u equals 0. They gave a combinatorial way of computing this based on bordered Heegaard Floer homology. And they proved an exact sequence, that if you have a framed knot, there's some exact sequence of the surgery exact sequence, basically. Y0 and Y1 are the surgeries of K according to whatever your framing you picked. So it kind of increments the framing by 1. Some more results. In Dye and Manolescu proved that involutive Heegaard Floer homology is computable for 3 manifolds obtained by plumbing along almost rational graphs. And so for me, the only recognizable 3 manifolds here are the Seifert fiber homology 3 spheres, which all live in this family. So basically, Dye and Manolescu computed the Floer homologies of all Seifert fiber homology 3 spheres. And so then there's some more computational tools that I've summarized. That I'll summarize, like basically Hendricks, Manolescu, and myself, we proved a connected sum formula, so that helps you get more examples. If you know the involutive Heegaard Floer homology of Y1 and Y2, we gave a simple algorithm, a simple formula for what it is on the connected sum. The ordinary Heegaard Floer homology of the connected sum is just the tensor product. And so actually the involution is also just the tensor product of the 2 involutions. We proved that a while back, and I shortly, or within a year or something, I wrote down also there's some tensor product for the knot versions. The involution isn't just the tensor product, but it's a little bit more complicated, but it has a formula for the tensor product, just kind of from the chain complexes and their involutions, there's some formula. So these are kind of computational technique tools that we have. So this is kind of the point of the talk, is we're going to summarize the results we've proven. So this is the sort of more recent work with Hendricks, Holm, Stoffregen, and myself. We proved this surgery exact sequence, and we proved another one, which if you know how Oshvath and Szabo's mapping cone formula is, you'll recognize So this one is if you have a knot. The second one is if you have a knot in an integer homology 3-sphere Y. We proved this exact sequence, which is you take the end frame surgery, and then you add like a big M to it. And you have some exact sequence like this, where you have, it goes from Yn to Yn plus M. It increments the framing by M. And then instead of, and then the kind of the third group you need is some twisted version of it. But I guess, you know, this formula might not make a lot of, might not like really speak to you, but the important thing is that this is kind of the main ingredient in the mapping cone formula, this exact sequence.
So just to get the picture here, the second statement is, let's see, so in a more specific case, when the 3 manifold is an integer homology 3-sphere.
Mm-hmm.
And in that case, you can prove more, right?
Yeah.
You can prove that for a given n, and the m, those are just any n and any m, or the m depends upon n, or what's the relation?
So m usually is a positive number. Yeah, m should be a positive number. Yeah, positive integer. Mm-hmm.
Okay,
Yeah.
Great, thanks.
Yeah. That's right. Yeah, thanks. And so the bold coefficients are powers and f adjoin u. And there's some special twisted coefficients we put on HFI minus. The exact form isn't that important of what these are, but I guess the moral of the story is that this is kind of, Oshvath and Szabo proved an exact sequence like this for ordinary Heegaard Floer homology. And the mapping cone formula, the one with the A's and the B's, is actually just what you get by letting m go to infinity. In a very precise sense, that's how you obtain the mapping cone formula. Like that's, and so this is kind of the main ingredient of the mapping cone formula. And so here's kind of a first, so that's what we did. And so we proved a mapping cone formula for involutive Heegaard Floer homology. And so I'll tell you what exactly these maps are. So I call this also the weak version, which I'll tell you, this isn't quite enough to actually compute what the mapping cone is, but it's almost enough. And I'll tell you the extra little ingredient that's necessary. Though this one works for knots in any 3 manifold. So let's say any integer homology 3-sphere. So basically we have some cone, and we have on like the top and the bottom of this cube are just the ordinary mapping cones of Oshvath and Szabo. That's the ordinary mapping cone formula. And then this theorem is that kind of we can define a morphism between the top and the bottom. And kind of the top is like a one-dimensional cube. Like a one-dimensional cube is like 2 points in a line. And then the bottom is also kind of a one-dimensional cube. And a one-dimensional cube, kind of a morphism between one-dimensional cubes is like exactly like what you would, it's like, you know, an arrow from the top that goes from the feet of the horizontal arrows, and then an arrow that connects the tails, and then there's also kind of this homotopy. And so what you should think is that there's this category of cube diagrams called, I mean, they're hypercubes. And then kind of like what this is saying is that like we have these 2 one-dimensional cubes, and the involution is naturally described as a morphism between the top, from the top to the bottom in this category of cubes. That's kind of the thing that that's the best way to see it. Every statement, if you believe in maps between cubes being like, or morphisms between cubes being these sort of diagrams where you have arrows that like only increase the indices of the cube. If you believe that, then everything is kind of this formal, all the categorical constructions are like very motivated by just thinking in terms of cubes. And so kind of, this isn't that strong of a statement because I haven't actually told you how to compute any of the maps. I've told you that we can compute the DN map, but I haven't told you how to compute any of the other maps. And so we don't know how to compute. I haven't told you the secrets for computing it. But, you know, just, it's not, this form is not amenable to computations, but I will tell you a form that holds for knots in S3, which is amenable for computations. And kind of the secret is the following. Well, DN is Oshvath and Szabo's mapping cone formula. You just take the same map as theirs. HN, the key here is that this actually factors. It factors through one of these funny inclusion maps we talked about. Remember, A sub S is like Okay, remember, go back to this picture. Remember HN, like in the diagonal arrow goes from A's to B's. And so kind of the claim, the key is that it factors. It has this kind of factorization property that it factors through one of these canonical inclusion maps. So it's some map, it's V tilde, one of these inclusion maps from AS into into the tilde BS, I guess, followed by just some map that we don't really know how to say, like to give a nice description of. Per se, and then iota A is kind of, you take the not involution and you just kind of multiply it by power of U so that it has the right domain and codomain. Iota B is basically this map iota A, but it's composed with this canonical homotopy equivalence, or it's composed with a homotopy equivalence. But like basically the important observation is that these factors together, like if you have a cone with all of these factors for not in S3, the homotopy type of the cone is determined uniquely by all of these conditions. So there's some auxiliary information such as like this choice of homotopy equivalence and this choice of homotopy, but the package is well defined up to homotopy. Given any two choices, you can connect them by a morphism of cubes, which is itself like a three-dimensional cube. So for computations, this is like this is like enough to do the computations you would want. It's sufficient. So those are kind of, that's the strong version of the cone. It tells us how to compute all of the maps. There's a recipe for doing it, and you pick some maps that make it a cube in a certain way, and it doesn't matter which maps you picked. They all give you the same answer up to homotopy. And so in particular, like a consequence is this like involutive Floer homology of a surgery, just to summarize, is just determined by CFK infinity iota K, these two little bits of information. There's also forms for the rational surgeries like P over Q surgery, and also for zero surgeries. But they, yeah, I don't know, they're kind of just sort of similar. I won't state those, but here's a diagram to just tell you where the maps go. So here's the differential D1. Let's do the +1 surgery. So here's X. X1 is the surgery complex. That's what Oishwath and Szabo call it. They call it, this is like the cone from A to B. This is just CF S3 with +1 surgery coefficient of K. And so here's iota X. So this is basically, our theorem just tells you that iota is something that looks like this. So iota A kind of takes A0 to A0. It switches A1 and A-1. It switches A2 and A-2. And on the B's, the coefficients are slightly different. Like the B's, like B0 is interchanged with B1, B-1 is interchanged with B2. And then we have these homotopy terms. And so it kind of has this nice spiral picture. I don't know. It's fun to look at, but it's a very like concrete thing to compute. Yeah. I guess another thing I would like to say, that I would like to just go back a little bit. One thing was really important to understand just when looking at this homotopy is that like kind of the Q direction is this vertical direction. So there's two ways to interpret this. One way is that involutive Heegaard Floer homology is isomorphic to some cube that looks like this. As a chain complex, it just is some chain complex that looks like a cube. Another way, and kind of the better way to think about it, is actually that the involution on CF minus is gotten by just summing all the arrows that have a vertical component. So the top is like CF minus of yn, the bottom is CF minus of yn, and kind of the involution is just all the vertical arrows. Well, I guess that's how I would think about it. And so there's the cube. And so there's some more properties that we want to talk about. There's this like sort of property of turning an iodic, of taking the involutive not Floer homology take the process of taking the involutive not Floer homology and building this involutive surgery complex can be just codified into like a sort of functorial package. If you want to talk about just these algebraic categories of iota complexes and iota K complexes. So basically an iota complex is like a complex over F adjoint U, which has an involution, it squares to the identity up to homotopy. And an iota K complex is kind of the knot version. It would be all the properties that involutive knot Floer homology has. So you have some chain complex with two, oh, something in the chat. What the horizontal grading, i.e. the indices, let's see. Melissa, could you explain your question a little bit more?
Yeah, hi, sorry. So I'm imagining, like, I just wanted to check that when you had that complex and you drew A as being in this quadrant and B as being this half plane, I wanted to check, like, does iota actually flip? It's hard for me to imagine how, like, B minus 1 is being taken to B2, you know?
Oh, yes, no, that's a good question. That's a good point. See, that's right. That's a great point. See, the thing is, if we go back, it's a little tricky. It's like not super intuitive, but somehow it's like the right thing to do is the following. So iota B, right? So B is like a half plane. So it's the composition of iota K, which you should note like switches like kind of the vertical half planes with the horizontal half plane. But then you actually also already in the mapping cone formula, you have this kind of canonical homotopy equivalence between the horizontal half plane and the vertical half plane. So it's the composition of these two maps is the thing. So remember the differential d sub n, you have like one of the maps is one of the inclusions followed by, we often call it the flip map, like you flip from maybe the horizontal to the vertical. And that already appears in the mapping cone formula. So in the B side, you need to do the same thing. You do the canonical, you do iota K, and then you follow by the flip map. And so kind of it switches twice. So iota K switches from vertical to horizontal, and then you compose with the flip map. And that somehow turns out to be the right thing to do. Where were we? Okay, so one thing that we considered this operation just like purely algebraically. And so if we have, we'll say is that an iota, just an algebraically defined iota K complex, just purely defined algebraically, it's L space type. If it's homology, the homology of what you would call B sub S is just F adjoint U. And the reason we would call it this is because if you have a knot in Y, a knot K in Y, the homology of B sub S for the knot complex, for the actual knot, is just the same as the homology of the knot, the three manifold that the knot lives in. And so in our case, like if we have an algebraically defined one, you just make the same condition. Like what algebraically would it be if it was from a knot in an L space? And so what we proved is that there's sort of this algebraically defined map, which we call XI algebraic, which sends an iota K complex of L space type to an iota complex, just algebraically what the mapping cone would look like. And we proved that this is just a well-defined map on the level of homotopy type. So if you take two iota complexes, which are homotopy equivalent, then if you take two iota K complexes, which are homotopy equivalent, there's kind of this algebraically defined knot surgery model, which is also well-defined up to homotopy equivalence. And the key is that on the surgery model, we use these kind of algebraic properties, this factorization property. And that's the key that determines this. That it's the homotopy factors in this way that you would expect. That's the key property that determines the homotopy type of the cube. And so let's see. Yeah, so building on the work of Dye, Hom, Stoffregen, and Trong, here's some applications. So here's an application, and we'll talk a bit about how we proved this application. But this is definitely building on the work of these authors, Dye, Hom, Stoffregen, and Trong, Dye, Manolescu, Dye, and Dye, Stoffregen. I mean, kind of some of the critical input is due to them. but we were able to kind of do the final computation to implement their program. We proved that the homology cobordism group is not generated by Seifert fibered homology 3 spheres. And so I guess previously there was work due to many authors, Freuschow, who didn't publish it, Francesco Lin and Matt Stoffregen, they constructed classes which are not Seifert fibered spaces. They're not equivalent to Seifert fibered spaces, but they didn't show that the Seifert fibered spaces don't span the homology cobordism group. They just found some classes which weren't Seifert fibered spaces. So like maybe the connected sum of, maybe you need like connected sums of Seifert fibered spaces to generate everything. But because a connected sum of a Seifert fibered space might not be Seifert fibered. But they proved that we proved that they don't span the homology cobordism group. So homology cobord, they're sort of in some sense a small portion of the homology cobordism group. And this was really due to, I mean, this is due to the work of Dijkholm, Stoffregen, and Trong, or this one of the critical inputs of this, which was basically they characterized what the they gave an algebraic obstruction to something being in the span of Seifert fibered spaces. I mean, specifically what they showed is that, like, due to Dye and Manolescu, and I think expanded upon by Irving Dye, there's a classification of what the complexes of Seifert fibered spaces look like, but then Dye also showed what the complexes of all connected sums of Seifert fibered spaces look like. And so using the surgery formula, we basically were able to exhibit some things which we could show were not in the span of any of these spaces, up to the algebraic notion of homology, algebraic version of homology cobordism. And so another sort of application for computations, kind of what facilitates this is understanding a little bit, is kind of efficient computations of all of this. So if we have two iota complexes, we say they're locally equivalent if there's grading preserving chain maps in both directions, which commute up to homotopy with the involution, and their isomorphisms on homology after inverting U. And so kind of these are exactly what you would get if you had a homology cobordism. You would have maps in both directions. You would just take the cobordism map for, the cobordism in one direction. The other direction, you would take the cobordism and you would turn it around and reverse the orientation. And that would give you a map in the opposite direction. Note that we're not asking for these to be homotopy equivalences. It's weaker than homotopy equivalences. We don't require the composition of F composed with G to be anything recognizable. It just has to be an isomorphism after inverting U. And so basically, if we have involutive Heegaard Floer homology, or we have the chain complex with the involution, kind of all of the obstructions to homology cobordism can be encoded in terms of local equivalence. And so together with Hendricks, Halm, and Stoffregen, we actually were able to give some efficient computations for local equivalence classes of surgeries. So just recall before we state the formula that we have there's kind of this canonical identification of spin C structures with Z mod N due to N surgery. So if N is odd, I mean, this is now just arithmetic. If N is odd, then 0 is the only self-conjugate spin C structure. So the conjugation action on Z mod N is just I maps to minus I. So if N is odd, you can just think about it. There's only one that's fixed. But if N is even, there's actually two. There's 0 and there's N over 2. These are the only self-conjugate spin C structures. And so what we proved kind of a nice way to actually compute things. For applications, basically one will always use this formula. We proved that the local class of CF minus is just A0 iota K in the 0 spin C structure. So you don't need this like gigantic model of the mapping cone formula. You just take A0, and that simplifies the problem a lot because A0 is much smaller than the mapping cone model. The big mapping cone formula, and you don't have to make any extra choices to get the local class. You don't have to pick this you don't have to pick this canonical homotopy equivalence or pick the homotopy in the cone. You just use A0, and that really simplifies computations a lot. And then the other one is in the half spin C structure. We're actually able to also give a formula for it. It's slightly bigger, but you also don't need to pick any extra data. So the involution, it's locally equivalent to 2 copies of A sub n and 1 copy of B sub n. The differentials are like the inclusion maps, the canonical inclusions. And the involution on A sub n, the involution just switches the 2 copies of A sub n by the identity map. And it is the identity on B sub n. It doesn't do anything to B sub n, it's just the identity. And so that's actually, notice there's no iota k in there. It's just like this silly thing that like switches the 2. So there's not a lot of information in this one, but we do have a concrete formula for the local class. And so I guess one application oh yes, okay. A similar story holds for rational surgeries. If you're willing to sit down and enumerate spin C structures on rational surgeries, you'll basically, the same formulas hold if you're willing to figure out what the correspondence is. It's just like more bookkeeping though for spin C structures, but the same argument holds. And so as an application, well, we can compute correction terms. So D upper and D lower of a surgery in the 0 spin C structure, they're just kind of the correction terms of large surgery of the knot, plus some shift, which we encode as the D invariant of the L space, or the lens space LN1 in the 0 spin C structure. And there sort of is another one for the half spin C structure. The D lower is just ordinary D, because remember, like this local class had nothing to do with iota k. There was no involution. The involution was non-trivial, but it didn't have anything to do with the involutive complex. It just like was this silly like term switching thing. So kind of we can compute the D invariant, D upper and D lower. And I guess one sort of moral reason that one can see this is that like there's this paper by Ni and Wu where they showed that the D invariance of surgeries on knots in S3 didn't really depend on the surgery coefficient you took. It was all kind of just determined. There's basically just one piece of data, and then if you like computed it on +1 surgery, that was the most important thing, and then all the other coefficients were just a formal shift depending on the coefficient. And so this is kind of an analog of that. You know, we basically, they're determined by their values on like one surgery, and then everything else is gotten by like a shift is the moral. The moral of the story. And so there's a similar thing in the previous formula we had. Like, I'm just going to go back really quickly. Oops, that's not what I wanted back. So here, kind of like, you notice the local class doesn't really depend on really on what n is. It's just very small dependence on n. I guess in the half spin C structure, it's A sub n. There's a dependence, but like in the 0 spin C structure, there's no dependence on the surgery coefficient, basically. So those were some applications of the formula that we managed to prove. And I guess I will subject you all to an idea of how the proof goes. So the proofs of, which maybe is a bad idea, but, oh, actually, hold on. Do I have till 50 after, or do I have until the hour?
Probably like 5 more minutes, and then because some of us have to do things at 4. But
Okay. Okay. I just have a tiny bit more, so I don't even know if I'll finish. Have 5 minutes, but well, okay. I'll finish. I won't go till the end, though. I'll just go like for a couple more minutes, and then we'll wrap up. So the mapping cone formula, kind of, how does this work? Well, there's 2 components of the old proof, which is the large surgery formula, and then this like funny exact sequence where you have like these 2 parameters n and m. And we basically proved both of those with Hendrickson and Stoffregen. And so we have those components. And so we basically, what we're going to do is, let's just focus on the case m equals 1. So let's just describe how one might prove this exact sequence, because that's the main step. And we'll do it on the case where we just increment it by 1. And so the idea is that you want to define a cobordism map, which goes from the n surgery to the mapping cone of the n+1 to the unsurgered thing. So you want to think of this as a cobordism map. Notice that if you have a map, like if you had a quasi-isomorphism like this, you would just take the ordinary exact sequence for a mapping cone, and then you just like replace one of the terms. Like, so the mapping cone, there's an exact sequence that has like the domain of the mapping cone, the codomain, and the actual cone. And so if you have a quasi-isomorphism to the cone with something else, you can just like delete the cone and you just put in the other thing. And if you note that when you do that, you just get the actual exact sequence you're looking for. So the idea is to define a quasi-isomorphism between the CFI of yn to the cone, the mapping cone. And use the exact sequence for mapping cone from homological algebra, and you're done. So basically, you actually want to define a map from this guy to the cone. And so kind of the idea to do that is you build a diagram like this. And it's called a hypercube of chain complexes. And kind of on like the top and bottom faces are the diagrams that Ojvath and Szabo used to define as in their proof of the exact sequence. And so then the next step is to add in all these other maps. The purely vertical maps are just going to be the involutions. And then you have kind of homotopies between all of these things. And then there's a long arrow that kind of relates various compositions in the diagram. And yeah, the maps along the top and bottom are Ojvath and Szabo's maps. And actually the front and left faces were basically constructed by Hendricks and Manolescu. And the challenging map that it doesn't follow from any of these constructions is this long length 3 map, which you would need to, if you wanted this theory, you know, if you wanted this to be a proper map, you would need to kind of have a length 3 map that goes from the top left to the bottom right. And basically the way you should think about this is like, if I make the left-hand side, like such a diagram kind of determines a map between the stuff that I've drawn as red and the stuff I've drawn as blue. If you just kind of think about what this diagram represents, it's exactly a chain map from the red thing to the blue thing. And, but the red thing is exactly CFI minus of y sub n, and the blue thing is exactly a mapping cone of some cobord. It's exactly the mapping cone of some cobordism. So the whole game amounts to building these cubes that look like this, and then and trying to ensure that these cubes satisfy certain properties. But I think that's all I want to say about the construction or about the proof. So I'll just thank you for listening.
Thank you. Is there any question?
Might be kind of a dumb question, but your examples of things that are not in the span of Seifert fiber spaces.
Oh yes,
maybe-
there's. I didn't state those. Yeah.
Is there
So
anything
there's
interesting to know about what 3 manifolds those actually are?
Yeah, there are surgeries on knots. They're kind of, we had to take some connected sums of knots and then we did surgery on them. So I could tell you exactly what the examples were. They were surgery on the connected sum of T613 minus 2 copies of T67 and the cable T2325. So some odd connected sum. Yeah, I mean, it's more, we thought more algebraically about it, like tensoring things together and trying to get pieces to cancel until we got nice terms, but nice formulas for things. I don't know if we have like a really geometric understanding of like why these were the ones that worked, but somehow when you tensor these together in this way, you get an interesting knot complex for some algebraic reason. I don't know if there's some geometric significance to it.
Like, could surgery on a prime knot give you an example?
Probably, actually, I don't really see any reason why it wouldn't, but the thing is that we only really know iota K for certain examples. Like we only know it for torus knots or L space knots in general, and thin knots, like alternating knots, and a few other families. But usually the knot Floer homologies, the way we compute these involutive Heegaard Floer homologies is just there isn't enough room for any interesting involution on the complex. And so it's just like the complexes usually aren't that interesting from the algebraic perspective. Like they're not that complicated. And the only way to get more complicated one is to take. I don't think there's any reason it couldn't be a prime one. It would just have to be outside of the ones we know how to compute using sort of these techniques.
Great, thanks.
So maybe I have a technical question as a non-expert. So this kind of mapping cone formula from Heegaard Floer, so do they correspond to any kind of surgery on the Lagrange in the symmetric product?
Yes, I think so. Like they're kind of, you could realize it maybe as, you take like, you can formulate them in terms of exact sequences of Lagrangians, sort of. Like you could make like they do have some interpretation. Like if you take, there's like 3 Lagrangians and you have a map from in the Fukaya category, you have like a morphism from one of the Lagrangians to the cone of the other 2 by some map. There's a way to interpret it that way. And so that would be there. You can, if you read like Ojvath and Szabo's paper, maybe not the first paper they wrote, but one of the later ones. If you think about it, it is an exact sequence. It is sort of like a quasi-isomorphism from one Lagrangian to the cone of another, where the cone, I just mean it's like this diagram where you have like one Lagrangian and you have a morphism, which is an element of the Fukaya category. It's like an element of Floer homology, sorry. And then to the other one. And so like, if you just were to formally write down like, what is an equivalence between 2 diagrams in the Fukaya category, it would be like, you have a map from one to the other, and then also a map from in the opposite direction. And like, you just do the same categorical things you would do. You want the compositions to be homotopic to the identity. And all the compositions, like you can just, it's like Fukaya category things, like it's the compositions in the Fukaya category. So you can phrase it that way. And then like, kind of that's like the alphas in the surgery formula. And then you just kind of pair with the betas, and that would give you an exact sequence. So there is some like Fukaya category interpretation of exact sequences.
So
I don't know if that's what you were asking, but that's the closest.
Yeah, that's exactly what I was asking. So I was just curious that because you have when you introduce the involution into this Floer homology, I mean it's something like a equivariant theory, and for those I don't know about a exact sequence that is so.
I don't have an interpretation in terms of the involutive one in this sense, like, because when you do the involution, yeah, I don't know, because involution isn't really acting on a symmetric product. It's not acting on the, like the same, you're kind of going through different symmetric products. And so I don't know, I mean, maybe there's some very beautiful way to describe it. I don't know though, certainly that would be great. I don't know what that would look like though. I mean, somehow, like, it's like a little magical that it works out. Like, probably there's some really nice way to describe it, but like, it's complicated because, the involution involves lots of moves in a Heegaard diagram. So the Lagrangians are changing a lot. And so, it's not like you have an action on some, I don't know what that would look like. That's a fun question though.
Thanks.
So if there is no more questions, let's thank our speaker again and then take a 5-minute break and come back for the tea time. That sounds good. Thanks, Ian.
We come
Thanks,
back
everyone,
to
for
the same
coming.
Zoom.
Yeah, I'll be here.
Yeah, I have to go for another meeting. So Ian, thanks a lot. I'll be in touch next time around.
Thanks for coming, Dave.
Yep, see ya. I'm gonna stop the recording so you can have tea off the